Okay. So what we are doing is that we are solving the continuity equation at the cell center itself, and we are solving the momentum equation as a center. And that's what we do.
एक सेकंड रुको जरा, लैपटॉप में इतना प्रॉब्लम हो रहा है। सेकंड। Hello, am I audible and the screen is also visible?
Yes, sir.
Okay. Let us start in this manner. Excellent. Is my screen visible now?
Yes, sir. Now it's gone.
Hello, am I audible? Is my screen visible?
Yes, sir.
चलो शुरू करते हैं. So today we are going to talk about the semi-implicit method for racial linked equations. So as Arpan has said before, that there are two concepts. One is basically the concept of collocated grid, where we are basically solving both continuity and momentum equation at the cell centroid. Similarly, when there is a staggered grid, so what we are doing is that we are solving the continuity equation in the cell centroid. And the momentum equation at the surface. At the surface. So what is the requirement of going for this kind of an arrangement where we are basically solving the continuity equation here and the momentum equation at a staggered point? So when we discretize the equation itself, so A equals to A in B U in B plus uh, some source term, if it is there in the Navier-Stokes equation, and plus or minus dp dx, if I'm actually considering it to be a one-dimensional equation as of now, and then this dv, and then there is a control volume integration over it. Okay, so this AEUE is basically equal to ANB UNB. Okay, so what are these? NB are basically the neighborhood points. Okay, and AEUE is basically this east face. So small e is basically the east face itself. Is it clear to all of you?
Yes, sir. But sir, earlier you had said that pressure term itself is part of the source term.
I'm actually writing it in a separate manner. So this is some kind of heat source or something like that. But in case of Navier-Stokes equation, this dpdx actually becomes a part of the source itself.
Yes, sir.
So let us remove this. You can remove or you can write in a general format as B plus this thing. Okay. So it doesn't matter. You can separate the pressure term from the source term itself. Okay. So then plus of B, I'm actually considering it to be 0 in my case. So this actually becomes minus of dp dx multiplied by dx into dy into dz. Okay. So this dx actually gets cancelled out. So this actually becomes minus of, so it will be like this dy and dz will actually form the area. And this minus p, if I actually integrate over that 1D point itself. So if it's a case of a collocated grid, for example, I'm solving the momentum equation and the continuity equation at the same cell centroid, at the same cell centroid, then it actually becomes like PE minus PW multiplied by area. Okay, so area is basically dy into dz, which you are basically integrating from. Okay, or you can convert this thing into an area integral also as for you and me. That can also be done. So in our case itself, that dy into dz actually forms our area, and dp dx gets cancelled out, and minus of dt actually give you that P minus pw. Okay, is it clear to all of you?
Yes, sir.
Okay, so then if I actually have a checkerboard kind of arrangement where the values are basically 0, 100, 0, 100, 0, and 100. So my cell of interest is this one, which I'm actually demarcating by using a hatch line. Then it actually becomes, this one is your east face, this one is your west face. So if I want to find out the value at the east and the west face, as I have said earlier, what we do is actually we express this east face as a mean of P plus PP divided by 2. And similarly for the west face itself, I write it as PP plus PW divided by 2. Is it clear to all of you? That's a central difference formula, by the way.
Sir, this is for checkerboard condition, sir.
Yeah. Checkerboard arrangement.
Yeah, okay, sir. Okay, sir.
Arrangement. Okay. So now if I actually pull the values here, you will see that PW minus PE multiplied by area. So it can be further reduced as PW minus PE divided by 2 multiplied by area. Okay. So PW is basically 0 because this is capital W and this is capital E, which is 0. So 0 minus 0 divided by 2 multiplied by area. So this is giving me 0. Okay. Hello, am I audible?
Yes,
Yes,
sir.
you are audible. Sir, I just requested you for about a minute. My connectivity was dropped here. So I will request you to just for a moment, if you can go to the previous slide, just to glance and again come back. So that will be helpful. That is request.
So what we are doing is basically this one is a discretization of the Navier-Stokes equation. So AEV equals to sigma of A and B U and B plus of B plus of minus of dpdx multiplied by delta V. Okay. So what we
Okay.
do is basically we take a general transport equation and then we integrate with respect to that of dV. Okay. So then what we are doing is that A and B is basically your neighborhood cell centroid. Okay. And small e is basically your E cell phase. Okay. So what we are doing is basically this AEV is basically equal to sigma of A and B U and B and plus of minus of dpdx multiplied by dx into dy into dz. So if I simplify this term itself, it actually comes out to be minus of T minus PW divided by multiplied by area. So this is small e and this is small w. Okay. So there is a minus sign there.
This
Then
is pressure terms, sir, or no?
pressure term, pressure term.
Okay.
So PW minus PE multiplied by area itself. So this actually comes out to be like this one. And then this is by using central difference formula, I am actually expressing this cell faces as a function of the neighborhood cell centroids. I'm putting it down there in the equation itself, and then this is becoming 0 for the checkerboard kind of an arrangement. Because PW is 0, PE is 0, but PP is 100. So this equation is not taking into account the local pressure gradient. This is only taking into account this PW minus P divided by 2, which is coming to be 0. So if I actually use a central difference formula for a collocated kind of a grid arrangement, then I'm not going to get a pressure sensitive equation. Okay.
Okay, sir.
So then going to the next slide itself. So what we are going to do is that we are going to solve it for the staggered kind of grid itself. So if this is a staggered grid, then in equation actually reduces to PP minus P divided by multiplied by area. Because instead of that, now you're staggering the grid in the right hand side direction. Okay. And this one is a initial cell. So if I actually staggered it in the right hand side direction, so PP minus P multiplied by area, that will be. So this is P, this is capital P. So this will be 100 and this will be 0. So 100 minus 0 multiplied by area. So now the source term actually takes into account the effect of the pressure on the Navier-Stokes equation. Is it clear to all of you?
So, sir, we are
Yes, sir. Clear, clear.
integrating. So we are
Hmm?
integrating in the staggered control volume, right? That is why you wrote PP minus PE.
Yes. So the continuity equation will be solved here, the initial control volume here, and the momentum equation will be solved in the staggered control volume. Okay. So now if I write the control volume here, draw the control volume here. So this is P, this is E, and this is small e. So AEUE is basically equal to sigma of A and B U and B plus of B plus of AE PP minus PE. Okay. Then if I actually simplify it further, U is basically equal to A and B U and B divided by A and A plus B, that can be written That can be written down like that. And this is equal to E by small a Pp minus Pe. Okay. So this A by small a, I'm writing it down as small d. Is it clear to all of you?
Sir, just one small query.
बोलो.
This you are taking from for assignment 9 solution part of that.
नहीं मैं पढ़ा रहा हूँ. मैं असाइनमेंट वगैरह नहीं देख रहा हूँ अभी. इसके बाद मैं असाइनमेंट चालू करूंगा.
Okay, because if you could cover something of that, that will be helpful for us in solving the assignment in time. So
Okay.
that will first.
I will try to do first cover the theoretical part, and then I will go to the practical problems.
Okay, sir. Okay, sir.
Okay. So this one is basically, I will call it as an exact, like the true solution itself. So E, P, P, P. When there is no start, I'm considering it to be a true solution. And then I'm kind of trying to guess it. Okay. So this actually becomes star. So A EV star equal to A and B even B star plus P plus A PP star minus P star. So the variables without star actually gives you the exact value, and this one is basically your gauge value. Okay. So you actually take a gauge value at the pressure itself, and then you actually find out the velocity from the momentum equation. So if the value of pressure is actually a gauge value, then the value of velocity that you are getting, that is also a gauge value. Do you agree with me?
Sir, can you
So
repeat
this one
once?
is, so this one I am considering it to an exact equation. Okay, यहाँ पर start नहीं है ना, UV, UNV, PPP. So this I am considering is a exact variables. मतलब pressure और velocity दोनों accurate है equation में, ठीक है. But मैं जब equation solve करना शुरू करूंगा, तब तो accurate नहीं होगा ना. So I have to take some guess value and then I have to find out the pressure, the velocity itself. So what I do is basically in the momentum equation, I assume some pressure over the whole domain, which is called initialization, and then I try to predict the velocity. Okay. So if the pressure itself is a guess value, then the velocity itself also becomes a guess value. Is it clear to all of you?
Yes, sir. Like iteration, right? Will be.
Iterations.
Yes,
Yep.
sir.
So this one is the guess E star. This star actually means guess value. And over the period of time, at every iteration, you see that whether the value of velocity and the pressure changes over time or not. So if it doesn't changes over a period of time, then you consider it to be your solution to be convergent. Okay. Is it clear to all of you?
Yes,
Hello, am
sir.
I audible? Okay. So your solution then becomes A equals to EV minus EV star equals to sigma of A in B, UNB minus UNB star plus of AE, PP minus PP star minus of PE minus PE star. Is it clear to all of you? So what I'm doing is basically I'm subtracting your exact equation from that of the approximate one. Okay. So this is basically EV minus EV star. So this I'm considering it as EV prime, EV minus EV star. So this prime actually means deviation variables. Is it clear to all of you?
Yes, sir.
Okay. So this I'm considering it as deviation variables. So this actually becomes A equals to, or A EV prime equals to A in B U in B prime plus of A E PP prime minus PE prime. Okay. So what we are going to do is that if I want to, for example, if I want to find out the value of the variable itself, so E star plus of some this right hand side of the equation, okay, that I have to find it out in order to find out the true value of EV. EV star I already know because this is the guess value that I've taken while starting solving the equation itself. When I was, I think you can turn off your mic. I think what is happening. Someone is not muting their mic and random noises are coming and it is kind of irritating to me. Dhananjay, you can switch off your mic. So EV equals to EV star plus RHS. So this is called the RHS itself. So RHS, if I'm going to solve it out, I have to know the value of P prime and PE prime. Okay. This PP prime and PE prime I have to know in order to find out the value of EV prime. So if I actually know the value of EV prime, I can add the EV star, my initial guess value, with the E prime itself in order to get EV. Is it clear to all of you?
Yes, sir.
Okay. So in this equation itself, I actually said that in this algorithm, I said that this is semi-implicit equation for pressure linked equations. Okay. Semi-implicit method for pressure linked equations. So why it is semi-implicit? So what we do is actually we actually ignore this term, the first term on the right hand side of the equation, and we take this term and this term into account. Okay. So if I'm actually ignoring this term itself, so then what we have to do is that, for example, x equals to z plus 1. Okay. So if I'm considering z to be 0, so I have to over approximate y in order to get it equal to x. Okay. So y must compensate the value of z to get equal to x. Okay. So my equation actually reduces to EV prime equals to AE by AE PP prime minus PE prime. This is equal to DE PP prime minus PE prime. Is it clear to all of you? So we are basically not taking the influence of the neighborhood points while determining the value of this EV prime itself. So it's a kind of assumption we are taking in order to simplify the whole equation. So if I know the value of this PP prime and PE prime, I can directly put it in the equation itself and then I can determine the true value of EV. Okay. So which is basically your value at the value of the velocity at the staggered cells in front is small e itself. Is it clear to all of you?
Yes, sir. Yes, sir.
Okay. So do you have a can you make a wild guess that from which equation we are going to find out the value of this PP prime and P prime? So what do you think that how do I get the value of these deviation variables of the deviation value of the pressure itself?
Poisson equation.
No, from the continuity equation. So this continuity Poisson equation can be used, but in general, in case of simple algorithm, we don't involve the Poisson equation, because Poisson equation we can basically that satisfies the continuity and the momentum equation itself, but kind of that's a different set of solvers. We don't use it in the simple algorithm, but that's another kind of approach. So another approach is basically another one is a projection method. So if time persists, I will introduce those things to you. So the continuity equation actually becomes, if I write it in the Cartesian coordinate system, this actually becomes like this, equal to 0. Okay. So now this, then I have to integrate with respect to both time and space. So this is basically your 0 to t, and then south to north, and then west to east, and then sorry, this is top to bottom, and this is t plus delta t to t, and then you have to kind of integrate with respect to that of dt, dx, dy, dz. Okay, plus of, and then this t to t plus delta t, and there is uh, bottom to top, and then south to north, and then east to west, okay, east to west, and this ddx of rho in dx, dy, dz, dt. Okay, plus of t to t plus delta t, bottom to top to bottom. Similarly, this east to west, north to south, and this dy of rho v, dy, dx, dz, dt. Also, similarly, I can do the integration in that manner, which is dtz of rho w, dz, dx, dy, dt. Is it clear to all of you?
Yes, sir.
Okay. So this can be further modified into rho p minus rho p naught, delta x, delta y, delta z divided by delta t, plus of rho u e minus rho u w delta y into delta z, plus of rho v n rho v tau delta x into delta z, plus rho w v minus rho w bottom delta x to delta y equal to 0. Okay. So now, as you have seen, this is UE. So UE is basically equal to UE star plus EE PP prime minus EE prime. Similarly, this can be written as U W star plus of DW PW prime minus PP prime. Okay, is it clear to all of you? So what we are going to do is that we are going to put that momentum equation down in the continuity equation, and then we are going to create an equation involving the pressure term itself, and then we are going to find out the value of this PP prime, PE prime, and PW prime by solving for all the cells in the domain, and then we are going to put it back in this equation itself, and then we are going to get the velocity from there. Okay, is it clear to all of you?
Yes, sir.
Okay. So this APPP prime equals to AEPE prime plus AW PW prime plus A in PN prime plus A is ES prime plus AT PT prime plus AB PB prime plus some source. So A actually becomes rho E dE delta Y delta Z. AW becomes rho W dW delta Y delta Z. AN becomes rho N dN delta X delta Z, and AS becomes rho S ds delta X delta Z, and A B becomes rho B dV delta Y delta X delta Y, and AT becomes rho T dt delta X delta Y. Is it clear to all of you?
So this whole thing should be valid for compressible flow also, because you have not considered incompressible condition.
That can be done by using compressible के लिए मैं लिख रहा हूँ ठीक है, but
Yes, yes.
this can be reduced to an incompressible one also.
But this is valid for all condition, right?
Huh.
Hmm.
So rho P naught minus rho P delta Y delta Z delta S delta Y delta Z divided by delta T plus rho W E W star minus rho E EV star delta Y into delta Z plus rho S B S star minus rho in V N star delta X into delta Z plus rho B WV star minus of rho T WT star delta X into delta Y. Okay, is it clear to all of you? So what this source term actually means? So first term is basically temporal variation of mass flow rate inside the control volume, or you can say it to be mass accumulation. We'll say it's mass inside the control volume, temporal variation of mass inside control volume. And this one is basically your mass flux along X. This is mass imbalance, I will say. Imbalance along X. Second one is basically mass imbalance along Y. And this one is basically mass imbalance along Z. Is it clear to all of you? So if my solution actually converges and the flow itself is incompressible in nature, then this actually becomes zero. If incompressible. If incompressible, and the solution reaches steady solution. So if incompressible and the final solution is steady. Is it clear to all of you?
So I want to ask something. This B term, it looks like integral form of the continuity equation itself. So, okay, if B tends to zero, we get a solution, means the solution converges. But does it really depend, like flow is compressible or incompressible on B going to zero? I mean, I think B goes to zero for all kind of flows.
Uh, I think if the solution itself is unsteady in nature, then your density actually becomes a function of time if the flow itself is incompressible and unsteady in nature. Then you actually don't get this term to be equal to zero. Okay,
Uh, yes,
but the
yes,
other
that is
terms will be equal. The other terms will be equal to zero.
yes, sir. Means even for yes, sir.
Okay, so then what is simple algorithm? So let me gist it. So this is basically what? First you guess the value of P star. Okay, then solve the momentum equation. Equations to get U star, V star, and W star to get P star, and then solve for P prime equations. That is a continuity equation. Because you know the value of E star, you can easily get the value of the P prime itself. Then what you do is basically you kind of use J3 to find U, V, and W. Since we know that U equals to E star plus of D, dp minus B. This is small e, this is small e. Okay. In the first step itself, so you correct P. So P, how to correct? That is basically P star plus P prime. Okay. So then you actually go to step number 1 and iterate till convergence. Is it clear to all of you? Hello, am I audible?
Yes, sir. Yeah. I mean, we find in step 4 we find UVW, but the solution converges only when B goes to zero, right?
B equals to 0. And what you
Yes.
see is basically your U at next time step. If it's a steady solution, so U at t plus delta t minus of U at t divided by U at t should be less than epsilon. So epsilon is your relative convergence criteria. Is it clear to all of you?
Yes, sir.
Others in the class, do you have any uh, kind of doubt regarding the thing that I've taught recently? Hello, am I audible?
Okay, sir.
Okay. So there is another thing which is called the Poisson equation that I'm going to derive for you. So that's actually one of the things you actually require. So there are different approaches you can solve a solution by. So one is basically the simple algorithm, another one is a pressure projection method, another one is a Poisson equation. So I'm going to now derive the Poisson equation. So let us consider steady incompressible flow field, steady and incompressible flow field. Okay. So then the momentum equation actually becomes rho v bar u. So v is basically the velocity vector and E, V, W are basically the components of the velocity in the x, y, and the z direction respectively. So this is equal to del dot mu grad V minus of dp dx minus of dp dx. So which is basically equal to this minus of rho V bar V del dot mu grad V minus of dp dy, and this is minus of rho V bar W del grad of W minus of dp dz. Okay. So then what we are going to do is that we are going to reduce this equation. So the main idea of what I will say is basically of solving this kind of equation is that, for example, if there is a flow field and we have a scalar which is flowing with the flow field, for example, the concentration of the pollutant or some kind of aerosols are actually flowing in the domain, and then you actually have another equation for this one. Plus del dot grad phi plus this. Okay. So basically, the number of variables which are present in the domain are basically E, V, W, T, and phi. Okay. So phi can be a temperature field, that can be a concentration field. So we basically need another equation in order to make the degrees of freedom to be equal to that of zero. So in order to make it zero, we basically require one equation, so which is basically called the pressure Poisson equation. Okay. Another equation, which is the pressure Poisson equation. Is it clear to all of you? Hello, am I audible?
Yes, yes, sir.
So in order to derive the pressure Poisson equation, so what we have to do is that we have to take the divergence of all these equation itself, the momentum equation 1, 2, and 3. So what we are going to do is basically we are going to make a derivative of ddx of first equation, ddx y of second equation, and ddz of third equation. And then what we are going to do is that we are going to add up this equation and use a continuity equation whenever there is a possibility. Okay. Since this one is an incompressible flow, so del dot v equal to 0 is our continuity conduction, our continuity uh, condition or mass balance condition. So if I actually use this del dot u, so this multiplied by dv equal to 0, we means that u dA is basically equal to 0. So which basically means that ua at the east face minus ua at the west face is equal to 0. Which means, for example, you have a tail like this, and this east face minus west face. So ua west face minus of this ua east face equal to 0. So this basically means that ua at the west face is basically equal to ua at the west. The east face and the west face, the value of ua at the east face is equal to that of the value of the ua at the west face. So which is basically your volumetric flow rate is conserved. So there is no mass accumulation inside. Okay. So is it clear to all of you?
So it's continuity equation, right?
It is a continuity equation, which is basically your volumetric flow rate conservation. So the
Income.
volumetric flow rate at the incompressibility condition. Is it clear to all of you? So what we are going to do is that we are going to put these ddx of del dot rho vu is equal to tail dot mu grad of u minus of dp dx. So I have to do the ddx of the whole x momentum equation. So how to do it? So ddx of is, it will be I cap ddx of plus j cap ddy of plus k cap ddz of minus of rho u square I cap plus, so rho should be outside since I'm considering this the condition for which I'm deriving the equation, that is basically incompressible and steady state in nature. So u square I cap plus u j cap plus u w k cap. Okay, so this is equal to ddx of uh, I cap ddx of plus j cap ddy of plus k cap ddz of. Okay, so this multiplied by mu of du dx I cap plus mu of du dy j cap plus mu of du dz j cap minus of dp dx. Okay, is it clear to all of you? So the left hand side of the equation can be further reduced into ddx of, this will be ddx of u square plus ddy of uv plus ddz of uw. Okay, so now as I've said earlier, I will always look for the opportunity in order to use the continuity equation while taking the divergence of the momentum equation itself, and then I will try to reduce it. So this is equal to ddx of u du dx plus u du dx. Since it is 2u du dx, so I'll actually separate it out. So you will understand what's my intention as of now. So why I did it. U du dy plus w du dz plus u dw dz. So ddx of u, and then you actually take it to be like du dx plus dv dy plus dw dz plus u du dx plus v du dy plus w du dz. So this is equal to ddx of, this term will be equal to 0 as per the continuity equation. So u du dx plus v du dy plus of w du dz. Is it clear to you? Hello, am I audible?
Yes, sir.
चलो, इसके बाद क्या होगा? Equals to ddx of so I will do the derivative. So this will be equal to du dx into du dx. Let me write it again so that I can also do it from here. So du dx du dx plus q d square u dx square plus dv dx du dy v d square u dy dx plus dw dx du dz plus w d square u dx dz multiplied by rho. So this can be further, I will kind of try to simplify it. So as of now, I've actually kept the left hand side of the equation as this one. So now I will go to the right hand side of the equation and try to simplify it further. So if I actually go to the right hand side of the equation, that is equal to d dx of del dot mu grad v minus of dt dx. So this is equal to d dx of I cap d dx plus j cap d dy plus k cap d dz dot mu of du dx I cap plus du dy j cap plus du dz k cap minus of dp dx. So this is equal to d dx of mu d square u dx square plus mu d square u dy square plus mu d square u dz square minus of d square v dx square. Is it clear to all of you?
Yes, sir.
Then what I'm going to do is basically I'm going to I have shown you that how I actually took the ddx of that of the x momentum equation. So now I'm going to add the ddx of x momentum equation with the ddy of y momentum equation with the ddz of z momentum equation, and then I'm going to find out that how does this simplify. So if I actually write it down, so it will be, so you can try it out at home. So as of now I am doing it for you. So rho of du dx plus u d square u dx square plus dv dx du dy plus v d square u dy dx plus dw dx du dz plus w del square u dz dx. And this plus of rho du dy dv dx plus u del square v dx into dy plus dv dy dv dy plus v del square v dy square plus dw dy dv dz plus w del square v dy dz plus rho of du dx sorry du dz dw dx plus u of del square w dx dz plus dv dz dw dz plus v del square w dy dz plus w del square w dz square. तो बीच में टर्म मिस होगा, तो which is dw dz dw dz. So then what I'm going to do is I'm going to uh, take the terms where I can use a continuity equation. So this one is a place I can use a continuity equation, this one is a place, and this one is a place itself. So as you can see it from here, so if I actually add them up, so it actually becomes u of dx of del dot d. So this is equal to 0. Similarly, I will take these terms, which are the coefficient of this v itself. So this one, and this one, which actually reduces to v of d dy of del dot t, which is also equal to 0. And similarly, if I take the last term in the equation itself, uh, this term, and this term, so it actually becomes w of d dz of del dot t, okay, del dot t equal to 0. Okay. So now what I'm going to do is that I'm going to simplify this equation. So uh, watch me together. It's an hand system. So the equation we reduce it to, so rho of du dx plus q of that term is gone. It actually becomes dv dx du dy plus of dw dx du dz plus of du dy del v del x plus of del v del y del v del y plus of del w del y dv dz plus of du dz del w del x plus of del v del z del w del y plus of del w del z del w del z. Is it clear to all of you?
Yes, sir. Yes, sir.
Others in the class?
Sir, can you please repeat this long step?
Which one?
This whole thing, sir. I mean,
Whole thing, yes, sir.
whole thing means you wrote do by do x del dot u equal to 0. The three equations you wrote, and this after that, sir. I mean, the last line only.
The last, this line.
Yes, sir. Yes, sir.
That I actually wrote after eliminating this components itself. This thing, and this thing. मैंने तो सिर्फ simplify किया, ठीक है? And now I'm going to that of the right hand side of the equation itself. So mu of ddx of u del square del square u del x square plus of del square u del x square del square u del y square and del square u del z square plus of mu of ddy of del square v del x square plus del square v del y square plus del square v del z square. Similarly, the last term in the equation itself, which is this one, there is another term, the pressure term itself, x square plus of del square w del y square plus del square w del z square minus of del square p del x square minus of del square p del y square minus of del square p del z square equals to mu of del square del x square. If I take the common from it, that is the first this term, this term, and this term. So it actually comes out to be like d dx. So what I'm doing is actually I'm putting this outside and then I'm putting this inside. Okay. So this can be done in case of partial differential equation. So this will be equal to that of du dx plus dv dy plus dw dz. Okay. Like plus of mu of del square d del y square du dx plus dv dy plus dw dz. Similarly, plus of mu of del square d del z square multiplied by du dx plus dv dy plus dw dz dw dz minus of del square p del x square plus of del square p del y square plus del square p del z square.
Sir,
And
but
then
this term is
which bola
though
sir?
you by is only a u component only, right, sir? Other component also will come.
Uh, other will be yes. UVW is there. ना ठीक ही तो है. UV and W. So I take this term and this term. उसके बाद मैं dx square d square by dx square बाहर ले जा रहा हूँ और बाहर वाला डिफरेंशियल अंदर ले जा रहा हूँ तो ठीक ही तो है ना
Okay, sir.
गलत
Okay.
है
Okay.
so this is equal to 0 this is equal to 0 and this is equal to 0 so now your equation actually reduces to minus of del square p okay so now this can be further reduced to 1 by rho del square p del x square
Sir,
plus
can you go
1
for the last slide a little bit?
ah,
Just last slide for a moment.
last slide में गया हूँ ना बोलो
Oh, so just okay, ठीक 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 है, please
1
proceed.
by rho please so the right hand side of the equation left hand side of the equation reduces to this one this is equal to minus of u dx plus of du dy dv dx plus of du dz dw dx plus dv dx du dy plus dv dy dv dy plus dv dz dw dy plus of dw dx du dz plus dw dy dv dz plus of dw dz dw dz. This is a pressure point equation. Is it clear to all of you?
Yes, sir.
Others in the class?
Yes, yes.
After this derivation, you will be covering something for from assignment 9 also that will help us for solving it.
इसके बाद मुझे असाइनमेंट 9 देखना पड़ेगा मैंने नहीं देखा है भाई देखने के
Because
बाद मैं बता पाऊंगा ना
हाँ तो थोड़ा सा it will help us in completing the assignment in time. If you take it next session, then in that case it will be difficult.
हाँ वो करता हूँ मैं करता हूँ
Our request
तो
for
दिस इज ठीक है मैं समझ रहा हूँ ना Fisher-Poiseuille equation. So this one is basically called the Fisher-Poiseuille equation. Okay. So there are five equations, there are five variables. So you can solve. So the variables are basically EVW, EN5, and one continuity, three momentum, and one pressure pressure. So this is how it works. So for this kind of problem, pressure pressure equation can be used. So now I'm going to discuss about another part of it, which is basically what do you mean by turbulence and laminar. So that part I have not discussed yet. So what do you mean by laminar flow and what do you mean by turbulence? Okay. So laminar flow. Laminar flow and turbulent flow. So do you have any idea what is the difference between a laminar flow and a turbulent flow?
Turbulent is more chaotic. Reynolds number is generally high compared to
What do
laminar
you mean
flow.
by chaotic?
It is not in the form of streamlined layers. From that point of view, I'm saying it is chaotic. So Reynolds number gets affected.
Is it predictable?
No.
If it is not predictable, it is random in nature, then we call it to be chaotic. So turbulent flow is chaotic in nature. So one of the primary signatures of turbulent flow is that we get multiple. It is chaotic in nature. And there are multiple length and time scales. Length and time scale. So this is a signature of a turbulent flow. Whereas laminar flow has single length and time scale, and not chaotic in nature. Okay. So even we call it to be turbulent flow to be chaotic in nature. For example, our atmosphere itself is chaotic in nature. But we also say that tomorrow there will be a rainfall, or in the summer the average temperature is this one. So if it is chaotic and unpredictable in nature, why we are able to predict it, the weather itself?
We perhaps try to fit it in certain boundary conditions or initial conditions. And
We
thereby, with some approximation, we predict the performance.
That's not the case itself. Even we actually have a simplified boundary condition also. The flow itself will be chaotic in nature. So for example, there is a turbulent flow itself, the turbulent flow through a pipe. So the flow will be, if I actually plot out the average velocity, so it will be somewhat like this. But if I actually plot the average, the instantaneous velocity, which is basically the sum of the average velocity and the fluctuating component, I will see some fluctuations like this. Okay. So even if the thing is chaotic in nature, we can see one thing is that the mean itself actually have some predictability inside it. So for example, if the summer temperature is somewhat like this thing, we know that the average temperature is going to be somewhat like this. So this average, the sense of average actually we get after doing the time average of the instantaneous variable over a large amount of time. Okay. So this U is basically for the temperature. If I take the time average of it, that will be equal to, or any variable field phi bar equals to 1 by T phi dt, 0 to T. So T is my time frame of averaging, and phi is my variable. That can be a vector, that can be a scalar, vector or scalar. Okay. So T should be large. So for example, if I'm actually doing the time averaging for that of the, for example, if I my somewhat like this. So if I do the time averaging up to this thing itself, maybe some 6 months or 1 year, the value of the fiber will basically not be same as that of the fiber for 2 years. But I should increase it on and on. So that fiber for 5 years, when I actually see like fiber of 5 years is basically equal to that of the fiber of the 6 years, then I can say that my statistical convergence has been reached. Okay. Is it clear to all of you?
Yes, sir. Yes, sir.
Okay. So you can mute off your mic because in the meantime I actually get sounds and which is a bit irritating for me. So I think you can mute off. Okay. It will be helpful for me. So that's how you actually get the statistical convergence. Okay. And so fiber is basically equal to 1 by T, 0 to T, phi dt. Okay. So T is my time frame for averaging. Okay. So that is basically my time frame for averaging. So then if I actually write the Navier-Stokes equation, so ddt of rho uu equals to mu del square v plus minus of drag p plus rho g. So if I actually solve this equation for that of the instantaneous field itself, the instantaneous velocity and the pressure fields. So one thing I can do is basically I can decompose the velocity field into a fluctuating and a mean component. And then I can take the time average of the whole equation. And the equation, the reduced form of equation that I get is basically called the Reynolds transform equation. So which I'm going to solve it. So ddt of rho u is equal to ddt of rho u plus u bar u prime is equal to, if I take the time average of it, so u prime average is basically equal to 0, by the way. So for example, if I take the fluctuating somewhat like some are positive, some are negative. So if I actually take this some are positive, some are negative, and the time period is itself large, so then the time average of the fluctuating velocity actually becomes 0. So my reduced form of equation will be this term will be equal to rho u bar. Okay. So is everyone clear with this thing? So then del dot rho u is basically equal to del dot rho u bar plus u prime, and then u bar plus u prime. So if I take the time average of this also, so this actually becomes rho of u bar plus u prime, and the bar of whole. Is it clear to all of you?
So this is also you're considering for incompressible case, right?
Yes, yes. So then mu del square v, if I take the part of it, u velocity, So mu is basically equal to del of u plus u prime u bar mu of del square u bar. And then if I actually take the grad p also, so if I take the time average of it, that will be equal to p bar plus p prime and average of that minus of grad p bar. Similarly, rho g will be a constant since I'm considering it to an incompressible flow. Otherwise, I have to consider like rho equals to rho bar plus rho prime, okay, which I'm not considering here. That can be done. So then my equation actually reduces to, if I actually go to this equation, so it will be ddt of rho u plus del dot rho u bar plus del dot rho u prime bar equals to mu del square u bar minus of grad of p bar plus rho g. Is it clear to all of you?
Sir.
So the third term in the left hand side of the equation, this is called the Reynolds stress. So how many variables you have in this equation? If I write the time averaging of the continuity equation, so let me do that also. So ddt of rho u, sorry, d rho dt a rho plus del dot rho v equal to 0. So del dot rho u bar plus u prime, and you take the time average of it. So it will be like del dot u bar equal to 0. Okay. So how many variables are there? So the primary variables are u bar, v bar, w bar, and pressure. Secondary variables are u prime, v prime, u prime, u prime, sorry, u prime square, v prime square, w prime square, and then there is u prime, u prime, u prime, v prime, v prime, w prime, and there is w prime, v prime. So how many variables are there?
6 under secondary.
Total कितना है?
Total there will be 10.
10 variables are there. Okay. So how many equations are there?
4 only, right?
4 equations. One continuity, 3 momentum equation, 1 momentum equation for each direction. So 10 minus 4 will be 6. So you actually require 6 equations in order to solve this set of equations. 6 equations extra in order to solve these variables. To get all the variables itself. Okay. So what we do is basically we assume that u prime bar is basically equal to mu t del v plus del v transpose this. And mu t you can find by using different model. For example, K epsilon model. C mu is basically equal to 0.09. K is the turbulent kinetic energy. And epsilon is the rate of dissipation of turbulent kinetic energy. Okay. So what we are going to do is basically we are going to express this Reynolds stress as a function of the velocity gradient. So this is basically called the Gaussian approximation. but this mu t you are going to find it by using k omega model, k epsilon model, or for the RSM omega model you are going to directly solve the transport equation for each Reynolds stress feature present here. So multiple approaches can be done, and that way we actually have equation for every Reynolds stress. So there will be 6 extra equations. So the total number of equations will be 10, and the total number of variables will be 10. So therefore your degree of freedom is 0, and then you can solve it. Is it clear to all of you?
So what is that mu t thing?
Mu t is basically your turbulent viscosity. So there are two viscosities you will get here. So mu t is a turbulent viscosity, which is a function of k and epsilon in case of k epsilon model, or which are basically, I will say, they're basically function of the fluctuating velocity and the fluctuating velocity gradients. And mu laminar, which is basically your physical property of the fluid. Okay, physical property of the fluid. So if I actually use this equation, so this actually becomes, if I actually reduce it, so ddt of rho u bar plus del dot rho u bar equals to mu laminar plus mu turbulent del square u bar minus of get t bar plus h. Okay, is it clear to all of you?
Mu t is mu l and mu t are added in turbulence.
Yes, yes.
Sir, but where is the fluctuation part, sir? That goes away. I mean,
फ्लक्चुएशन क्यों? अरे फ्लक्चुएशन तो यहाँ से चला गया ना, फ्लक्चुएशन को तो मैंने यहाँ पर चेंज कर लिया ना बॉसनिक अप्रोक्सीमेशन करके.
oh yes, sir, sorry, sir.
इसको सिंप्लीफाई करोगे तो ऐसे ही आएगा. So is it clear to all of you?
Yes, sir.
Okay. I think we can stop as of now. If you have any doubt, you can ask me.
Sir, can you elaborate something on assignment number 9? Some help will be there for us for solving. We are only halfway in that. So,
मुझे एक बार देखने दो, अगले क्लास में दिखा दूंगा कैसे करना है, ठीक है?
but then, sir, actually, we are requesting little help for solving it before time. The assignment due date
अरे
is actually
कब
24th itself.
24?
हाँ, assignment
अरे
9
भाई
date
पहले
is
से बोलना चाहिए. लास्ट मोड में बोल के क्या होगा ना, मुझे भी तो, मेरा भी तो काम है ना. मैं देखता हूँ मुझसे हो पाए तो, मतलब इतना कम टाइम में मैं कर सकता हूँ तो टाइम मिले तो कर दूंगा, नहीं तो तुमको ही करना पड़ेगा. You should have mailed me earlier. मुझे मेल कर देते, मैं बैठता.
Sir,
असाइनमेंट
our
9
request is that whatever assignment due dates, जिसका assignment due date अभी चल रहा है, going on. So if you can cover something of that before that in your problem solving, that will be some help for us in solving it little better way. And
हाँ ठीक है मैं करता हूँ, बट लास्ट मोड में बोलोगे तो कैसा होगा ना. मैं असाइनमेंट 9 का देखता हूँ हो पाता है कि नहीं कम टाइम में.
this we are
बिकॉज
requesting for assignment 9, 10, 11, 12 for all four subsequently. Before उसका जो due date है, उसके पहले if you can cover something, some that will be of some help for us also in solving.
अरे ठीक है मैं देखता हूँ. मैं वो असाइनमेंट 9 देख के रखता हूँ, उसके बाद मैं बोल देता हूँ कैसे करना.
And same request for assignment 10, 11, 12 also subsequently, because थोड़ा सा help solve will be of it will facilitate in completing it थोड़ा सा in a
ठीक
better
है,
way.
मुझे एक बार देखने तो दो भाई, मुझे एक बार देखने दो, मैं करता हूँ.
Okay, and then one more thing, just I thought I will try to know from you. Assignment 6, 7, 8 marks when they will be given?
असाइनमेंट 6, 7, 8, असाइनमेंट 6, 7, 8 तो देखो, असाइनमेंट अभी तक मैंने नहीं फ्लोट किया है, ठीक है. मुझे बोला गया था कि मैं अलग से फ्लोट करूंगा, ठीक है. वो अभी तक मैंने नहीं किया है, ठीक है. तो बाकी जो कंट्रोल कार्ड है उससे पूछना पड़ेगा, देखना पड़ेगा. आई थिंक इन ड्यू टाइम यू विल गेट इट, यू डोंट हैव टू वरी अबाउट इट.
Okay, and contents of this today's session will be available when मतलब on if one wants to review it again थोड़ा सा
हाँ तो मिल
और
जाएगा ना, तो वीडियो अपलोड हो जाएगा, कोई दिक्कत नहीं, इस हफ्ते में हो जाएगा भाई.
अच्छा sir, the final exam is will be consisting of what combination of questions, how much will be the coding part, objectives, multiple choice, and how would it be, if you can say something
फाइनल
on that.
फाइनल क्वेश्चन आई एम नॉट गोइंग टू फ्रेम इट, द प्रोफेसर ऑफ द कोर्स इज गोइंग टू फ्रेम इट. So I think he will be able to respond to it. But I think you can go through the syllabus. I think there will be no coding part, but it will be much more theoretical in nature. Coding तो नहीं रहना चाहिए. But मैं एक बार देख लूंगा. I will confirm from my side. But I am not going to set up the final question paper. I am only with the tutorial itself, and that this assignment itself or nothing more than that. The final question will be set by the professor itself, himself.
Okay, because it
But
is generally
assignment, बोलो
a 3 hours exam, online exam. So
कितना कब है?
it is on October end.
हाँ तो अक्टूबर एंड तो बहुत टाइम है.
हाँ, but
हाँ
then
ठीक है, मैं देख लेंगे, मैं बता देता हूँ. मुझे एक बार देखना तो पुराना कुछ है तो मटेरियल मैं बता देता हूँ.
okay, and our sincere request to you that okay, assignment 9 is due date is day after tomorrow. There will be again assignment 10, 11, 12. Normally every 1 week they are there. So in your program problem solving session, if you can cover the assignments for which due date is yet to come. So normally
हाँ
you
मैं
take it on
मैं
Monday.
समझ रहा हूँ भाई,
So
मैं
that will be
समझ
of
रहा हूँ.
help for us in completing it. It will facilitate. So
मैंने
that
मैं
also
समझ रहा हूँ भाई.
coding also will be little bit cover the minimum requirement at least. So
इसके बाद मैं शुरू करूंगा. अभी तक थ्योरी हो गया है, इसके बाद में कोडिंग वगैरह जितना भी है. अभी तक थ्योरी जो हुआ है इट इज एनफ. इसके बाद असाइनमेंट वगैरह कोडिंग वगैरह जो भी चाहिए वो करना होगा, मतलब वो मैं कर लूंगा.
okay, thank you, sir. Thank you.
Okay, any conceptual questions you have from this class? No, sir.
थोड़ा सा just as a little clarity, I will request. In most of the cases, we are using gases in this, and which is we know it is a compressible thing. Still, our general assumption is that it is incompressible fluid. So, which are the key conditions under which it is air or other gases which are generally used in CFD analysis? Fluids are also there, of course, but uh, those are considered incompressible under what major considerations in all this CFD analysis?
It is incompressible if the Mach number is less than 0.33. That's actually one of the consideration we use. In normal condition, it is incompressible in nature, but incompressible starts to break down when it is non-isothermal in nature, and the density effects actually come into play. If the speed of the fluid actually increases, then it actually becomes incompressible in nature. So that can be quantified by using Mach number.
So Mach number should be less than 0.33. That is what is the main condition under which fluids like air we are considering as incompressible and doing entire analysis, whether under simple method or Mach method or any other analysis that we are doing in all
Yes,
several
but if
assignments.
it is non-isothermal in nature, then this Mach number condition will not hold, by the way. So if the velocity itself is low and then I'm considering this non-isothermal condition, then the density effects will come into play. By the way, this density is going to influence the velocity as well. This temperature is going to influence the velocity, and which is going to influence the incompressibility condition. So for
And normally
isothermal fluid,
with the rise in temperature, the density is expected to go down.
yes,
And then in that case, the obviously the compressibility aspect will come into the picture. It will no more be considered as incompressible.
yes.
And which
So
generally
it
is the
goes
case of
down.
air, which generally is
It
the
goes
case of
down.
predominant fluid like air, which actually is compressible.
हाँ,
But we are doing the entire analysis assuming it as incompressible flow.
कंप्रेसिबल के लिए न्यूमेरिकल ट्रीटमेंट अलग हो जाता है ना, तो मुझे सिंपल रखना है, इसलिए मैं कंप्रेसिबल इनकंप्रेसिबल पकड़ के कर रहा हूँ. अब कंप्रेसिबल के लिए न्यूमेरिकल स्किल्स वगैरह हार्ड ऑर्डर यूज करना पड़ता है, विच आर क्वाइट
What I'm
डिफिकल्ट
saying,
फॉर
sir,
यू
in
गाइस
most of
बेसिकली.
the assignments, this analysis, we are assuming it as incompressible, whereas predominantly the fluid that we are considering is air, which by nature is compressible, but still we are analyzing it as incompressible. That is what
हाँ
I'm
तो
just
मैं
trying to.
मैक नंबर हाँ तो मैक नंबर कम रखूंगा तो वो इनकम्प्रेसिबल हो जाएगा ना, तो
Mach
उसमें
number
क्या
का
दिक्कत है.
मतलब we are assuming low velocity regime.
हाँ लो वेलोसिटी रेंजिंग. अब कोई फाइटर जेट जा रहा है, उसके सामने फ्लो फील्ड मुझे कैप्चर करना है, तो उसके लिए मुझे स्कीम चेंज हो जाएगा पूरा. ये सब स्कीम काम ही नहीं करेगा वहां पर, डिफिकल्ट हो जाता है. इसलिए मैं समझा नहीं रहा हूँ, घुस नहीं रहा. न्यूमेरिकल ट्रीटमेंट्स आर डिफरेंट है. वहां पर शॉक्स वगैरह सब कुछ आ जाता है, वहां पर इक्वेशन चेंज हो जाता है, तो उसमें अलग सा चीज है. ये सिंपल है, इसलिए मैं पढ़ा रहा हूँ वैसे.
हाँ, I'm not referring, sir, yours is okay. I'm just trying to incompressible का जो रेफरेंस हम लेते आए हैं पूरा continuously since beginning. So I was just trying to get an elaboration on that. That's the only thing.
अब देखो, कंप्रेसिबल तुम्हें करना है तो इनकम्प्रेसिबल का जो मेथड है इसको एक्सटेंड करके कर सकते हो, कोई दिक्कत नहीं. मैंने तुमको बेसिक इनकम्प्रेसिबल वाला सिखा दिया, इसके बाद तुम्हें समझ में आ गया, ठीक है. इसके बाद तुम कंप्रेसिबल के लिए इसे एक्सटेंड कर लो, क्या दिक्कत है.
Hmm.
इसके बाद डेंसिटी वेरिएशंस का जो टर्म है इक्वेशन में डाल लो, क्या दिक्कत है. सिंपल एल्गोरिदम मैंने जेनरल के लिए दिखाया ना, तो जेनरल के लिए नहीं करता तो इनकम्प्रेसिबल वाला जो डीडीटी वाला टर्म जो आ रहा था कंटिन्यूटी में, वो चला जाता है, और क्या होता है. ऐसा ही है, ठीक है. यू कैन डू इट. आई डोंट थिंक दैट्स एन इशू, but the numerical treatment actually gets a uh, bit kind of complex because convergence itself is an issue when the flow itself is compressible in nature, when the flow velocity increases. Okay. So do any others also have any question regarding the things that I've taught today? Arpan, Pandya, anyone in the class?
No, sir.
Okay, I think we can
No
stop here.
question, sir. No question, sir.
Okay, so I will upload the meeting in short time. So then you will be unable to go through it once again. Okay.
Okay, sir. And once again, the request is that request you to cover the pending assignment. That is the one which is due date is yet to finish. If you can cover little bit of that before that time in your problem solving session, that will be of help facilitation and help for us in solving.
मैं समझ रहा हूँ भाई.
Okay, sir. Thank you.
ठीक है,
Thank you, sir.
चलो ठीक है, बाय. ओके बाय.
Okay, thank you, sir. Thank you.